So this is OS X running Parallels 5, and we're looking at 3 virtual machines. The virtual machine right here is a BootToRam. The virtual machine right here with the 1 is just a normal Ubuntu virtual machine. It's identical to the BootToRam. The number 2 is also just a copy. It's identical to 1. So what I'm going to run is these Pepsi test scripts that I made. What they basically do is they take random files from the user library and they MD5 some of them. That's all they do. So what you do is I exploded the Pepsi test on my desktop, and then I changed to the directory media PSF home desktop Pepsi scripts, because that's the shared Mac desktop that you have. So on 1 I start it, and it's going to start up a top screen. It's going to start up a screen that shows you how many processes you have at the moment, and it's going to start a GNOME system monitor. So make sure that you got the right ones on the foreground. There's going to be a whole bunch of files that come here. So I start the same one on number 2, and I make sure that I have the files in the right order I want them. Alright, and now I'm going to start it on so what these two are doing right now actually is they're waiting for the script to be run as master from the 3rd script. And these all share the Mac desktop, so they basically communicate via shared files. So the RAM one right now I'm going to run as master, and what that's going to do is that's going to generate a list of 4,000 files in the user directory, and then those will be MD5 summed by all of these in parallel and in random order. So they won't all MD5 them in the same order, but they will MD5 sum all of them. So I run this, and just like the other ones, it pops up the 3 screens. And what it's doing right now, if you look at this, it's doing a big find, and then it's sorting it. So it's sorting it. And what this will do right here is you just wrote a timestamp, okay? And now the other ones are going to be waiting on the same timestamp. So same here. And what happens is in a little while they're going to start going, and it's real obvious what happens when they start going, because the bottommost, or the window where you launched the Pepsi test from, is going to start showing a whole bunch of MD5 sums. So they'll start pretty much at the same time. Alright, so they started. You can see the files going like this. Now if we look at the RAM one, it has a spike where let me get the mouse. It has a spike right here where it made the generation of the list, and now it's doing a spike where it's actually doing the MD5 of the sums. So the load is going up right here. There's minimal wait, and it's basically it's even idle right now, and the reason it is because it's done. So it has done its 4,000 user lib files. You see that the processes, they went up to 182, 291, and now they're back at about 160 where they started. Now if you look at the other machines, they're up at 308 processes, and the reason that that's happening basically is because there's, what's the weight there? 70%. And what you're going to see here is the CPU is just kind of like being used, but not how it should. So both CPUs are being used somewhat, and the exact same thing is happening on the bottom right here. So the load is 100 and the weight is 83%. So the CPUs are being used, but not really. It's all hard disk contention. So this is a test to basically exploit hard disk contention, but the difference is kind of striking. So the RAM is long since done, and these go on for, I don't know, maybe up to 4 minutes. So the difference in time is like one took maybe 15 seconds, and the other two take 4 minutes. And when I only had one of them running in parallel with the RAM, this one took 1 minute. Now when I added another one, the combination of the two, they'll take 4 to 5 minutes. So just the same thing happens. There's nothing real magical here. You always have huge CPU weight, and it causes the CPU to actually just idle on disk I/O, and this one is doing the exact same thing. So this is just simulates kind of random I/O on a hard disk in the operating system, as opposed to in a BootToRam. So the BootToRam here, of course, everything's in RAM. It's just a lot quicker. So I'm going to stop it because this is just going to keep going, and I don't feel like wasting more video time. So this is kind of my proof. It's one of the only ways that you can actually prove that the BootToRam is significantly quicker than the traditional boot to hard disk. The reason you can't prove it most of the time, like I did tests where I opened like 1,000 windows, is because there's been so much engineering that masks hard disk latency. So no one's dumb enough, basically, to run the test that I'm doing right now, because everyone knows it doesn't work. Which kind of begs the question, how would software change if it was like this? How much easier would a lot of things be? You wouldn't have to keep hiding the hard disk. So that's the whole point in this. Alright.